So this is the second lecture in the discussion of algebraic structures. And where did we leave off last time? Last time we talked about sort of two kinds of algebraic structures. Ones that are sort of similar to groups and ones that are similar to rings. And the groups are, I guess, maybe I would call this a group-like, and I might call this one ring-like. Ring-like. And the group-like algebraic structures, well, in both cases, there involves a set, right? That's a set of objects. That's the set that constitutes the algebraic structure. The group-like algebraic structures have one binary operation, and the ring-like ones have two binary operations. So ultimately, the group-like structures, the most sophisticated one was the group itself, was a group, as opposed to we started with magmas and groupoids, but groups. And the binary operation for a group, if, say I called the set G, is from G cross G into G, and there's an identity element, so that it has an identity, and every element in the set has an inverse under this binary operation, and it's associative. The operation is associative, and those properties together made groups. And then you started eliminating these things one by one. And for example, the groupoid only has this, the monoid has this, and then the semigroup starts adding in inverses, and they all are associative, right? They're all associative. So those are the group-like structures. Then the ring-like structures had two operations. One was an abelian group operation, where the whole set was an abelian group under the operation of addition. So as before, there's an identity. In fact, I don't even need to spell it out. I just write there's an identity 0. There's an inverse, which is minus v of any element inside the set. The minus that element is considered the inverse element, and of course it's associative. But it also had a multiplication unit from which it was a monoid. There's a monoid under multiplication, and everything in the ring, ultimately the ring-like ones that went all the way to the most sophisticated one was a field, right? So it was a monoid, and it was also a division ring, which meant that everything had an inverse except 0, right? 0 is the exception, right? There's no inverse for the additive identity. And then to make it a field, it was commutative. So it's and of course it's always associative, right? It was always associative. The monoid made it associative. So this was the most sophisticated of the ring-like algebraic structures, was the field. Meaning sophisticated, meaning it had the most requirements. Inverse, it has an identity under the monoid operation, and then you added the inverse to make it a division ring, and then ultimately you made it commutative to make it a field. So the difference between group-like and ring-like was the number of binary operations that were available. In this case it was 2, and in this case it was 1. But one thing that made them the same is that they both had one set. There was only one set in play. So what are all the possible binary operations for a set? Well, you've got G cross G into G, right? So all these binary operations ultimately are maps that look like that, right? So now let's think about another algebraic structure that we already know about, the vector space. And is a vector space group-like or ring-like? And it's neither. It's actually a more complicated object. And you'll remember in a vector space, we had a vector space V was ultimately a set of vectors, and there is definitely a vector addition, which we know was associative and had inverses and had an identity, right? So all of that exists in a vector space. So a vector space, because of these things, is without a doubt an abelian group under the vector addition property. But something the vector space had that so far none of the algebraic structures we've looked at has, is it had access to the real numbers. If it was a real vector space, it had access to the real numbers, and we called that sort of the bin of real numbers, right? That's the way I phrased it, bin of real numbers. And I guess I don't need an apostrophe there, do I? Bin of real numbers. So we had two different kinds of maps. The addition map was a map from V cross V into V, but then we also had a scalar multiplication map, which I guess I could write as a dot, and that was R cross V into V. And this map is something that could never exist up here in the algebraic structures we studied because there's only one set involved. There's no bin of real numbers, so those maps aren't even possible. So now we want to talk about algebraic structures that have access to two sets and associated binary operations. So that is the subject of this lecture. So the first new algebraic structure we're going to talk about is called the R module. The R stands for ring, and module is a version of, basically a version of a vector space that's a little bit more general. So this is going to generalize vector spaces. So just as we had before, we had groupoids going to, I guess when they went to rings, which went to fields, right, skipping a few in there. Vector spaces would be out here, and R modules would be out here. So we're kind of looking at something in the earlier evolution of a vector space. So in other words, all vector spaces will turn out to be R modules, but not all R modules will turn out to be vector spaces. So what does it take to become an R module? Well, you have to start with a group, we'll call it G, and it must be abelian, and therefore we know it has a group addition, which is a map from G cross G into G. But we also must have a ring, and that ring has all of its properties, right? It has a property of abelian addition, which is R cross R into R, and it has its monoid multiplication, which is another map, R cross R into R, right? And of course, and just like I said before, those have their own rules and properties. But the R module is also endowed with a map R cross G back to G, and which is a fancy way, of course, always these Cartesian products are a fancy way of saying an element of the ring and an element of the group get mapped back into an element of the group. I guess I should make a different element of the group, where G and H are elements of G, and A is an element of the ring. And once you have this structure, now you have, and you also have to be able to, and you typically will write this as AG equals H, right? So we usually tend to think of ring multiplication, because this rule does not have to be commutative. And by the way, this would be called a left module. And if it was G cross R into G, you would have a right module. And it could very well be that this is a commutative rule, whatever these mappings are, in which case you have a two-sided module, I suppose. Now, it's important to understand, of course, that the ring does not need to be a division ring. The ring does not need to be a field, as I said. It only has to be a ring, and that's why this is more general. But otherwise, this is exactly like a vector space, right? Aside from the fact that this thing is not a field, which means it's not guaranteed to be commutative, otherwise it is a vector space. But we call it an R module when we are leaning on the fact that the bin of scalars is merely a ring. Now actually, just having this operation isn't quite good enough. I guess I got a little bit ahead of myself. You have to have all of this, but you do have to assert the relationship between this operation and these operations, right? And that relationship must be linear, and that's a separate assertion you have to make. You have to say that A times G plus H equals A times G plus A times H, and you have to assert that A plus B times G equals A times G plus B times G. Right? You have to assert that, and you have to assert that A times B times G equals A times B times G. And what's fun here is you've got to keep track of what multiplication comes from where. So if I were to change this and say, okay, the monoid multiplication is red, the monoid addition is red, the abelian group addition is blue, and the multiplication property here, this multiplication property will be, say, green, right? This will be green. So then we can fill these in. Well, which is the actual module multiplication property? Well, that's this one here, this one here, and this one here's module multiplication, and this one's also module multiplication, and this one's module multiplication, that's module multiplication, and that's module multiplication, and so's that, and so's that. And then the abelian group addition property is here, here, here. The I'm sorry, that my bad. That is not the wrong color, right? The abelian group addition property is here, 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 and the ring addition property, which is red, is this one. Is that the only one? Yes, and the ring multiplication property, which is red, is that one. So this is why keeping track of the context is asserted just like in computer science, right? You can overload an operator. The computer can figure out what you mean because the computer just looks at the two arguments. If I have a group element on the left and an abelian group element from G on the left and the right of an abelian addition operation, I know I'm dealing with this operation. If I have a multiplication with a member of the ring and a member of the group on both sides, well, I know that that is the modular multiplication property. And these things, I have to assert these things before I can actually claim to have a full R module. The R module has not only this modular multiplication, but it also has the modular multiplication that is completely linear relative to the ring addition and ring monoid multiplication and the group addition property. And the last thing we need to say is that the identity in the ring, which is going to be, say, 1, and I guess in order to do this consistently, I got to write 1 green times G equals G. You have to assert that the ring's identity operates as an identity on the members of the abelian group. That's an additional fact you have to throw in there. Because just because this is the identity in the ring doesn't mean that this mapping has to respect that identity. You see, this is the identity in a mapping that's R cross R into R, right? The ring, the Cartesian product of the ring in itself back into the ring. That doesn't mean that that identity necessarily is going to map all G's into G when you throw the identity into this Cartesian product or into this ordered pair. So you have to assert that. And when you assert that, then you finally have all the pieces in place to make a module. So an R module has this modular multiplication that is linear, that's what this stuff is, linear in all of the other existing operations, and it has this identity property. And that is what makes an R module. Right, now the next step is somewhat obvious, right? An R module can become a vector space. And the way you make an R module a vector space is you still have your abelian group, and your ring now is a field. It's a full-fledged field, which means it's a commutative division ring. Now, the distinction between R module and a vector space is simply that. It's simply the existence of inverses and commutativity. There must be inverses in the field, and the field must be commutative, and such as with the real numbers or the complex numbers. And once you have that, you can make you might call it an F module, but we usually call an F module a vector space, as long as F refers to a field. And that is the vector space we've learned so much about, right? We've been studying these things for a long time. There is an intermediate object, which you might call a division ring space, right? Where this field F is not a full-fledged field, it's just a division ring, which means it may not be commutative. And that would allow us to have the quaternions to have this algebraic structure. The quaternions is a ring, so a quaternion over a group G would always be an R module. But it's a little bit stronger because the quaternions are in fact a division ring. They're just not commutative. So there is a historical definition of vector space where a vector space doesn't require a field, it just requires a division ring. And in that case, the quaternion R module, or I guess you would call it the Q module, would be a vector space. But in the modern definition of what a vector space is, it's got to be a field, and so the so the real numbers and the complex numbers are in, the quaternions are not. And once you have a field, right, now you have, the field of course looks just like the real numbers, right? That's the whole point in some sense. You have an addition property, you have a multiplication property with everything has an inverse except 0, right? And therefore you can do subtraction, and division makes perfect sense, where division by 0, right, is illogical because 0 has no inverse, and now you kind of know why. So, you understand that 0 doesn't have an inverse, multiplicative inverse, or it doesn't have a monoid inverse even in the real numbers. But once you have a field, you behave just like the real numbers, and that's a very powerful thing. And it makes a big difference. There's a lot of proofs. Well, I shouldn't say too much because I'm not a deep expert on ring theory, but there are proofs that only work for vector spaces that do not work for R modules. And so that's why there's a distinction, right? There's a distinction because you can say a lot of things about vector spaces which you cannot say about R modules. In particular, vector spaces can be given a basis. Whether it's finite dimensional or infinite dimensional, it can be given a basis. R modules can only occasionally be given a basis. And that goes into the proof that all vector spaces have a basis actually leans on the axiom of choice. It's interesting. It's an interesting proof. It's way outside of this. It's not too hard to do, but it's just outside of what we're doing. But the vector space, if you're willing to start going into these set theory proofs, you can see that you can prove that every vector space has a basis. But that's not always true for an R module. So the distinction is important, and there are now two different types of algebraic structures we're talking about. So now we've got two algebraic structures, R modules and vector spaces. And they're very, very similar. In fact, I'm not even outlining the distinction except to say that a vector space is an R module where the ring is actually a field. So what's next? So let's look at one example of this that's relevant to our current studies. So we may remember that we talked about a vector field. A vector field. And we express the vector field, the way we've been doing it in these tensor lectures is we say we have a coordinate system on our space-time. I'm calling that x0 and x1, where we know that we have x2 and x3 out there. And at every point in the space-time, we erect a vector field v, or a vector space v, at every point. And they all have their own vector space. So if the point is P, we're talking about the vector space at P, which we usually call the tangent space at P, which we may call T with a little sub P. So if that's P, Q, R, then this one would be TR, TQ, and TP. And a vector field chooses one vector at each of these points in spacetime. At every point in spacetime, one vector in each of these vector spaces is singled out. And the way we wrote that down is we called it A as a function of spacetime, mu, del mu, and the way we partial mu. And the way we use the partial mu is that established a basis in every vector space at once. And that's what we just studied previously in this what is a tensor series as a representation of the vector spaces at every point in spacetime using the coordinate system that we've placed. So we place a coordinate system on spacetime, you know, x1 and x0, and x2 and 3. And once we have that coordinate system, we can talk about differential operators with respect to that coordinates. And of course, the vector field would act on some function, f of spacetime, and the vector field is a map. The vector field is a map from the functions, the infinitely differentiable functions on the spacetime, I'll call the spacetime M, to the the infinitely differentiable functions on the spacetime M again, right? Because it takes a function and it returns another function. And so that's how our vector fields work. So the vector nature of the vector fields we've already talked about. That comes from the additive property of the differential operators in each spacetime. So we might say, well, let's take a look at this C infinity M kind of closely. And one thing we have to understand about this set of all infinitely differentiable functions on the spacetime, which means functions of the coordinates, right? Functions of x0, x1, x2, x3, which is written functions of x mu, like that. That set of all possible functions of this on the spacetime, that's not a field. And the reason it's not a field is you might take two functions and you might create an abelian relationship between them by adding them pointwise. So f plus g is a function f plus g on the spacetime, but what you're doing is you're going to every point in the spacetime and you're adding f of x plus g of x together, and that is equal to f plus g of x. So you do a pointwise addition. Likewise, and you can use this, since this will be real numbers, right? That's a real number and that's a real number. This addition here, the addition we're interested in, is just real number addition. Likewise, you can do this for multiplication. We can say f of x times g of x is pointwise multiplication. And that will be defined as f times g of x. And so through this way you can define, now you're defining an addition on the set of all functions. So the C infinity of M is the set of all infinitely differentiable functions on the manifold functions as functions of the coordinates. I'm now defining the addition function here inside this set. I'm defining an addition function inside that set using the addition function of the real numbers. Likewise, I'm defining a multiplication on that set using the multiplication of the real numbers. And that's okay. The problem is that you cannot create an inverse. You can certainly create an identity. You just take g of x equals 1 and you have an identity, so that's fine. But you can't have an inverse, because you can imagine a function that goes through 0. And at that point, if you tried to do a pointwise multiplication and you're trying to get everything to equal this identity element, well, every time a function hits 0, you can no longer invert it. So any function that takes 0 as a value can't be inverted and therefore is not invertible. So you can define addition, you can define multiplication, you can define an identity, but you can't define inverses. So you can't even create a division ring. So this is simply a ring. It's not a division ring, and it's certainly not a field. And with that in mind, you could say, well, vector fields form an abelian group. I can add two vector fields together. That's not a problem, right? You just add the components. So vector fields form an abelian group. So what if I took my abelian group G and I said that equaled the vector fields, that equals all vector fields, and my bin of scalars was the C infinity functions on the manifold, or I should say on the space-time, which is a ring. Well, what I've created is a C infinity module over vector fields. Okay. Now, if I replace this with just real numbers, I would have an R module, and where my set G is all the vector fields. This is actually a vector space. This R module will actually be a vector space because R is a field. However, using the set of all infinitely differentiable functions, that is only a module and not a vector field. So there's an example of how you might apply this definition of a ring, of an R module that is not a vector field. That comes up in the work in general relativity. All right, so now we're going to talk about the algebraic structure that's called an algebra. And an algebra is probably the most complicated one we're going to deal with, and we'll stop with it. I'm not sure that there's actually any beyond it that are particularly important, but we have all the pieces in place to talk about it. Sometimes when you talk about an algebra, they list out all the properties, but we're going to bundle them up, and we're going to say an algebra is going to start with a vector space, which we'll call V, and it's going to and that vector space, I won't, well, I guess I should, since we just learned about it, I'll say, remember, it's an abelian group, right? That has an addition operation that it's abelian, and that is abelian, and it is a field, right? And that field, of course, has an addition, subtraction, division, and multiplication operations. Now, the vector space will have an additional map, right? We already have one map associated that built the vector space. That was vector addition, which was a map from, the vector addition was a map from G cross G into G. Now actually, I've already started a little bit of confusion. I named the vector space G, and then I said, oh, a vector space V, and then I said, oh, V has got a abelian group G and a field F. Well, the vector space itself is just this. It really is just G, right? I shouldn't do it this way. I should just call this a vector space G if I'm going to do it. But since I'm using vector spaces, you know what? I'm going to call it V because we've always called vector spaces V. So the vector space is the set itself. It just, we have to make sure the set has all of these properties and there's an associated field with that set in order to be a vector space. So so the vector space has this associated addition property, and it has this. But now we're going to give it another property, this multiplication property, which is also a map from G cross G into G. And the key point is that you have to be right and left distributive. This multiplication property has to be right and left distributive relative to this addition property. So if G, H, and K are elements of G, whoops. See, I'm still doing this, right? These should all be V's. Should all be V's. Because I'm going to V cross V into V, V cross V into V. So I now want G, H, F, all are elements of V. So I want G plus H dot F to equal G dot F plus H dot F, right? I want that. And I want it to be true on both sides. I want F dot G plus H to equal F dot G plus F dot H. So I got to have that. And it's got to be compatible with scalars. So the scalars come from F. So I'll say A, B, C are elements of F. I want A times G dot B times, say, H to equal A, B times G dot H. So notice now, this dot here is the dot between the vector product dot, right? This should be just BH. When I don't have a dot at all, I'm implying A dot G, but this dot is the dot that comes from the fields, right? It's this multiplication, this little X here. So it's all part of tracking what operations are what operations. So this is bilinearity. This means that this multiplication operation is bilinear. And that's what builds up an algebra. So an algebra is a vector space where you can actually now multiply vectors as well as adding vectors. So notice this doesn't have to be abelian. It doesn't even have to be associative. That's really interesting, right? G dot H dot F, right? That does not necessarily have to equal that, right? That does not necessarily have to be true. And this is the first time where associativity is just something you can have optionally. Remember, everywhere else, there was a demands for associativity everywhere in the construction of V, right? As we built V up, we had the group had to be associative, addition has to be associative, these properties all have to be associative in the field, and it was one of the first things we demanded, and a lot of the most fundamental proofs depend on associativity. But when we get to an algebra, associativity is totally optional, and in fact, almost all the interesting groups in physics are non-associative. So that's an algebra. Let's do one example. All right, I want to start by talking about the tensor algebra. And this will be our example of an algebra. It's not an easy example, but if you want an easy example, just go to any reference book on the subject. I advise you to do that. For example, you can see that the real numbers will form an algebra and the complex numbers will form an algebra, and there's all kinds of different algebras. Those non-commutative algebras, commutative algebras, there's just tons and tons of examples out there. The tensor algebra is important, though, because it's going to motivate our study of what's called P-forms, and P-forms are an important part of understanding intermediate and advanced general relativity. So it's a good thing to just sort of focus in on the tensor algebra. It helps us understand a good definition and example for an algebra, and it's also useful as we proceed in GR. So let's begin with the tensor algebra. So a few things to remind you. If we take tensor products of vector spaces, we will create a shorthand notation for arbitrary tensor products of a vector space V. We will call that V, the little tensor product symbol and the superscript, and followed by a number. And that number is how many of these guys there are. If there's n of these, then we will rewrite that long string of tensor products spaces, or tensor products in this form. Now remember, each of these is a vector space, and this tensor product is also a vector space, and we've studied that pretty extensively in our previous lectures here in this course. So that's how you do. That's how we're going to do a notation for a tensor product space. Likewise, we'll have a similar notation. Well, not a similar notation, but we have another type of tensor products another type of vector space that we need to remind ourselves about, and that's taking the direct sum of different vector product space, different vector spaces, v, w, x, say y, and we can take an unlimited number of these and create a direct sum. And the direct sum of a series of vector spaces is also a vector space, and that vector space is the set of all ordered pairs where let me move this down just a little bit, where it's a, I'm going to consider ones that go on forever for right now, but it could be finite. But the first slot comes from the first vector space. The second slot is a vector from the second vector space. The third from the third vector space. The fourth from the fourth vector space. Forever and ever and ever, right? And so if we called alpha, we might call this one A, we might call this one I, we might call this one, let's see, alpha, A, I, back of the alphabet, Z, something like that. And the set of all possible tuples like this forms the direct sum space. And the direct sum space has an addition property where A, B plus C, D equals A plus B, C, I'm sorry, whoops, too quick, A plus C, B plus D, where this plus operation, these plus operations here, are the plus operations associated with the individual vector spaces, and this plus operation here is actually the plus operation of this entire vector space. So we're defining the addition of the direct sum in this way. And likewise, we can define, and I've of course reduced this to just 2, right? That's just for an example, just to demonstrate. But of course, it extends to this infinite one just in the obvious way. And there's a scalar multiplication property, which will be, I got to be a little careful, right? I'm using this, I'm saying the addition property is a map, and then I'm sort of demonstrating an example of the map on particular elements. That's usually not the way it's done. You usually write the addition property as a map from, in this case, I would say V direct sum W to V direct sum W. And then I would, after I write this down, I would write down this example to show how individual elements of this vector space map to individual elements back into itself. So likewise, the scalar product A, B, C, if C is a member, so C is an element of the relevant field, which would be, say, real numbers, for example, and say the real numbers is your bin of scalar for this direct sum space, or I should say for this direct sum space. That's going to be CA, CB, where there's an implied scalar multiplication of the individual vector space V and W here. So that's how we get our direct sum. So we've reviewed now the direct sum concept here and the tensor product concept here. We've just changed the notation a little bit for the direct product. Now we're going to blend these things together and we're going to create a tensor algebra. So to begin, we define the actual set that makes the tensor algebra. And that set we're going to call T, I'm going to put a big dot here, V. That's the name of the set that's our tensor algebra. And it is going to be this massive direct sum, which I'll write n equals 0 to infinity, of these tensor product spaces that we had defined before, right? So this is combining those two ideas that we did on this page, right? It combines this notation here with this direct sum, with the only difference that we're actually creating like a big summation, direct summation operation. So this thing is going to equal V tensor product 0, direct sum v tensor product 1, direct sum v tensor product 2, etc., etc., etc. So now, then if we continue this, this becomes, if the vector space V has a bin of real numbers, this becomes the real numbers, right? This becomes an element of this, that becomes a set of real numbers. This becomes just the set V. This becomes V direct product V, etc. And we could go on, and then you would have V direct product V direct product V forever and ever and ever, right? So we're talking about this direct sum now, right? So what would a typical element, so this now is, this guy here is a set, and this is another way of representing that set, right? It's just a little bit tighter because we've got this notation. But this goes to this, which goes to this. What would be a typical element of this set? A typical element is going to be a real number A, right, where it comes right from there. And it's an infinite tuple, right? This becomes a vector, so we might write B mu E mu like that, right? This guy is a tensor, right? So we might write that one as C mu nu, right? E mu E nu, right? That would be a typical tensor. And then this one would be D mu nu gamma, E mu E nu E gamma, like that. Right? And it goes on forever and ever, and you keep getting higher and higher ranked tensors as you go farther along in this infinity tuple. I guess we should call it an infinity tuple. Right? And just as a reminder, of course, these are the basis vectors of these vector tensor product vector spaces, and we're calling the zero version of it just the field itself, the underlying field. So each of these must be a real vector space. And notice we're also doing this. So this blends everything because each of these vector spaces here are different. This is a different vector space than that. This is a tensor product space. That's a vector space of rank 1. This is a vector space, a tensor product space of rank 2, a tensor product space of rank 3. These are different vector spaces. These guys have their own addition operations, their own scalar multiplication operations. But we've created this direct sum, which of course blends them together. So I could add two of these guys together just by, because I'll be adding things termwise using this rule of, say, CD plus EF, going back to the simple version, is C plus E D plus F. If you see how this works, when I extend this to this infinite tuple, I'm going to be adding real numbers in the first slot, I'm going to be adding vectors in the second slot, and then if you extended this logic, I'd be adding rank 2 tensors in the third slot, and everything would agree because those additions are all inside these individual vector spaces. So that might be a typical example of an element of the tensor algebra. Now remember, the tensor algebra is a set, and I've only described what the set is. I still have to describe the properties of the set. We already got the addition property, by the way, so we've got that down. We know it's a vector space, so we've got that down. What else do we need? Well, we need, of course, so this defines our addition operation. Right? So we need to define a multiplication operation, not a scalar multiplication operation. The scalar multiplication operation is already built in. We know how to do a scalar multiplication for any direct sum, right? We've already got that, so maybe I'll call that one the blue. But now we need a multiplication operation that takes this set and brings it back into this set. So it's sort of a map from n equals 0 to infinity v n into, oops, not that, it's the Cartesian, it's the Cartesian product. So now I have a little Cartesian product of the same direct sum, n equals 0 to infinity v direct product n, into n equals 0 to infinity v direct product n, like that. So this is exactly the same as we had from the previous. We're looking for a multiplication operation that takes the Cartesian product of the relevant vector space and returns an element of the vector space. So we have to define that. We haven't defined that. We've only defined a scalar multiplication property, but we haven't defined this guy yet. So let's come up with a way of doing that. And I want to proceed with a certain amount of rigor, probably not as much as it deserves, but let's consider the n-tuple, a typical sort of n-tuple with empty slots for right now. And now imagine that I take some tensor. Say I took b mu nu. And I'm going to suppress, this is a good time to suppress the e mu tensor product e nu. It's a little bulky to carry it around, but we know it's there, and we know the order because we know the order of the indices up here has to match the order down there. So we kind of know it's there, but I'm going to suppress it because I don't want to draw it all the time. And that's exactly why they suppress it, by the way, in physics books, is they just don't want to write it out all the time. And it's logical. It's just confusing, and I've argued before, it's just confusing to introduce it that way. Anyway, so let's take this guy. This guy is an element of V tensor product V, right? And we want to understand it now as an element of our real big vector space, which, you know, I already gave it a name, right? I want to understand it as an element of T V, right? That was the notation I was using for this object here. In fact, I could have saved myself a lot of trouble here by just writing it as T V cross T V as a map to T V, right? This dot up here, the reason we put the dot there is there's some ambiguity with something called the total tangent space of a manifold. So I'm copying a text that I used that added the dot because it had just talked about it. But I like it. I like the dot. I think that's fine because we're talking about the tensor algebra. So we want to think of this. We want to think of this tensor, which is an element of this thing, but we want to think of it as an element of that thing. So we create this mapping. We create an injection map, and the injection map we can write as I, a little I, and in this case it would be I2, right? I2 will take elements of the tensor product space and map it into elements of our massive direct sum space. And it does it in sort of the obvious way, right? This guy is, well, I've already written it up here, right? This set, an element of this set looks like this. So what it'll do is it'll just take the element of this set and it'll put it in exactly where it belongs, which is right here. So if I took I2 on B mu nu, I'm going to get 0, 0, B mu nu, 0, 0, and all zeros forever, right? It just puts it in the right place, right? It just puts it in where it belongs. And because of that, I can actually write really interesting things. I can write I2 B mu nu plus I4 C alpha, beta, gamma, delta, right? I can write that down, and it's almost like adding, it's almost like adding a second-rank tensor to a fourth-rank tensor, which we know is wrong because they come from different vector spaces and there are no ways of summing different vector spaces. But once I run this injection operator, what have I actually done? I now have 0, 0, b mu nu, 0, 0, dot, 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 and I'm adding it to 0, 0, 0, 0, c alpha, beta, gamma, delta, dot, dot, dot. And what's that going to be? When I add those two together, I'm using this rule here, which I did in simplified version, right, with just two elements, but I use that rule extended to this infinite tuple, and I get, of course, the obvious answer, which is 0. I add these terms this way, right? I add these terms this way. I get 0, 0, b mu nu, 0, c alpha, beta, gamma, delta, 0 forever. So this addition property here is the addition property of the vector space TV. All right, so I can now create this injection map, but I need this injection map to sort of understand how that works. So the injection map is kind of an important idea, and ever so occasionally you will see books talking about this, and they will write down things like b mu nu e mu e direct product e nu plus alpha mu e mu, right? And this is this is absurd. We know it's absurd because this is from one vector space and this is from another vector space, and there really is no defined sum. However, what they actually mean is this. They actually mean, when you see that, if you ever see that, they really mean this injection mapping of b mu nu plus the injection mapping a mu. And now the addition property is this direct sum, is the addition property from this massive direct sum space. So don't let that fool you. It confused me for a while. I had a hard time understanding that. So I'm laying it out there. So you got this injection mapping that allows you to insert tensors into this, into TV. All right, so once we've done that, we do need to understand our multiplication operation, right? We have TV, which, since it's a direct sum, we already know so the direct sum has to be a vector space. That's the whole point. A direct sum is a vector space. So it already came with our addition operation, and it came with a scalar multiplication, and we figured those things out. And we've created this injection operation that will take they'll take tensor products and sort of insert it into the direct sum. So now we need to create a multiplication operation, our multiplication operation that takes the direct sum Cartesian product into itself. Right? We have to create that thing. So what we do is we note that so that operation is going to be the tensor product operator, right? This is a tensor algebra, and that tensor product is going to actually be this multiplication operation. And let's see how that's going to work. Well, we certainly know that if you're a member of VI, like that, and you do the tensor product with a member Bj, you're going to get an element of I plus j, right? And so that is completely, or I should say, yeah. So that is completely understood and easy to understand. We've got that. We've got that down. Now, what we realize is that using this injection operation, nothing really changes much, right? If I wrote injection operation I, V cross I, injection operation of j dimensions, I guess I should put that, V tensor product J, I should get injection operation I plus J on V I plus J. These things are sort of isomorphic, meaning this process where I take this vector space, tensor product with another vector space, it gives me a second vector space. Here, I keep it all sort of in the same vector space because this guy is an element of TV, this guy is an element of TV, and this guy is an element of TV. So this is actually kind of what we're looking for, right? We're looking for, so now you can think of this side as an element of TV, Cartesian product TV, and this side is just TV. So that's a mapping to TV, which is exactly the way we need to define our algebraic multiplication. So with these injection operators are what sort of help us make this happen. And that's the formal step that's missing from a lot of the descriptions of tensor algebra that I've seen out there, and I find it confusing. I find it difficult without it. So I've done my example with it included, and it does seem like a little stretch of formality, I guess, in retrospect, but I think it's important because if you really want to sit down and track all the relevant addition operations, you really need to do this, right? Because here we know that this is an ordered tuple, and this is an ordered tuple, and this is an ordered tuple, all members of this space. But here you're going from one vector space, you're combining two vector spaces to make a third vector space, where here you're staying all inside T star V. And that's the difference, right? That's really a critical difference. And without these injection operators, you really can't do that. But the good news is that these injection operators, it's all isomorphic. It establishes an isomorphism between these things. So you're not really changing anything, nor are you really inventing anything new to do that. It's really, in some ways, it's just a way of transitioning the notation into these, to exploit these massive ordered pairs, or ordered infinity tuples, not ordered pairs. Okay, so what next? Well, next you need to have an identity, right? The identity element. And that's actually not very hard because we'll just assert that this ordered tuple is the identity element. So that ordered tuple times any member of let's say alpha equals alpha, where alpha is an element of this. So we have to assert that, okay? So then what are we left with now? And the last part is linearity, right? We have to show that A, B mu, C mu nu, etc. When you use this is now the vector space, the multiplication operation of the algebra. When you use that against say D alpha, you have to show that this process is linear, right? And so what we're going to, the way that linearity is going to work is you just need to think of this as A direct sum B mu direct sum C mu nu. That direct product D alpha is going to be A direct product D alpha direct sum B mu direct product D alpha direct sum C mu nu direct product D alpha. Right? So that is going to express linearity when you have one guy over here. And then, of course, if you wanted A, B B mu, direct product B A mu, like that, it's really the same thing. It becomes A direct sum B mu, direct product B direct sum A mu, and you proceed to distribute. You just proceed with the normal distribution. This, by the way, is very, very similar to polynomials, right? If you had a plus x plus 3x squared plus 4x cubed multiplied by b plus 2x plus 7x squared, etc., etc. It's really the same idea. You end up, except that you actually, these addition properties, we keep thinking of each of these as a real number. So these addition properties, these additions are all sort of real additions. But when you think of these as polynomials, as you can't add them and you're sort of stuck leaving it this way, you could really redo this whole polynomial concept to a x 3x squared 4x cubed, and you could consider each of these its own vector space, and then you could define these operations, and it would be very similar. In fact, it would be identical. So we have the distributivity, we have the identity, we have the linearity, we have the vector space, we have the vector space addition, which is abelian, we have the multiplication, we have the unit. So that creates ultimately our tensor algebra. So this guy here, n equals 0 to infinity, v n, which is what we're calling tv. Now it is a tensor algebra. We have all these operations. Well, I should write down. This operation is actually the tensor product, right? It's a straight up tensor product operation. And ultimately, I mean, this algebra here, we're going to take subalgebras, little pieces of it, and create important algebras, the most important being the exterior algebra. And we'll talk about that not next time, but pretty soon.